So today we're going to look at the second lesson in Unit 4, which is Lesson 2-6, Higher Order Derivatives. I think you'll actually like this section. It's easy. Okay, so you have learned how to find the derivative of a function. So now you're going to find higher order derivatives, and that just means we're going to take a function and find its first derivative, which I've already showed you how to do. And then you're going to take that function and find the derivative of it. Take that function, find the derivative of it. Take that function, find the derivative, and so forth. What you'll notice in the notation is clearly that's the first derivative notation, y prime, that we've used before. Second derivative will have 2 primes. Third will have 3 primes. After that, we're going to start to put the number of the derivative in parentheses so it looks like an exponent. The reason why it's in parentheses is so that it doesn't look like an exponent, that we know it's something different. And of course, these are all the other types of derivative notations that you could be exposed to as well. All right, so example 1, we are going to find the first 5 derivatives of this function right here, 2x to the 4th minus 3x squared. So the first derivative should be easy. We're just going to take 4 times 2, reduce that by 1, 2 times negative 3, and reduce that by 1. So this is nothing different than what you have done before. So f prime of x is equal to 8x to the 3rd minus 6x. So that's our first. And then our second derivative is going to be noted by f double prime, that's of an x, equals. And so this time we're going to take 3 times 8, which is 24, and reduce that by 1, and 1 times negative 6, which is negative 6, and that goes away because it has a value of 1. So we get 24 x to the 2nd minus 6. So you're just finding the derivative over and over and over again. So this is our second derivative. F prime triple prime of x is equal to, so we're just going to find the derivative of this now. So 2 times 24 is 48x, and then the derivative of a constant is 0. And so this gives us our third derivative. And then now we're going to find f, or the fourth derivative, so f fourth derivative of x. And then 1 times 48 is just going to be 48, and of course the variable drops off. So this is the fourth derivative. And then finally the fifth derivative. F fifth derivative of x equals, and of course the derivative of any constant is 0. And of course we cannot find any more derivatives to this. There are only 5 derivatives to this function. You're always going to find that there's going to be one more derivative than the highest degree in your polynomial. So now you try it. I want you to pause the video. You are finding the first 4 derivatives. Whoops, it's not what I meant to do. You are finding the first 4 derivatives of this function here. So pause the video and then restart it when you're ready. Okay, so f prime of x is equal to 18x squared minus, that's a 2, minus 4x. So this is our first derivative. Then f double prime of x is equal to 36x minus 4. That gives us our second derivative. Then f triple prime of x is equal to 36. That is our third derivative. And finally, the fourth derivative, oops, got a little carried away there. The fourth derivative of x is equal to 0. That's it. It's that easy. It's not going to get too much harder than that. All right, so for example 2, make that a little bit bigger, straighten it out. Okay, so for example 2, we're going to find the value of g triple prime, so the third derivative of the g function, and we want to find the value of that derivative when t is equal to 2. So the first step is going to be to find the third derivative. So g prime of t is equal to negative 4 t to the third plus 6 t squared plus 1. So that's your first. And then g double prime of t is equal to negative 12 t squared plus 12t. That is our second derivative. And then finally, g triple prime of t is equal to negative 24t plus 12. So then our second step is going to be to plug in to g triple prime, our third derivative. We're going to plug in a value of 2 for every t. So negative 24, plug in that value of 2, and so that gives me negative 48 plus 12, and I get a final value of negative 36. So the value of the third derivative of the g function of 2 is negative 36. So now you get to try. All right, so you are going to find the third derivative of a new g function, as I'm trying to get this straight. For this function here, the third derivative when x is 1. So pause the video, do your work, and then restart it. All right, so step 1 is to find the third derivative. So g prime of x is equal to 4x to the third minus 3x squared plus 2. So this is my first derivative. Then g double prime of x is equal to 12x squared minus 6x, and that gives us our second derivative. And then g triple prime, which is our third derivative finally, is equal to 24x minus 6. So then step 2 is to substitute in 4x, our value of 1. I'm going to put a 1 in for our x. So that gives us 24 minus 6, which is 18. So in example 3, we're now, oops, I just made it crooked again. There we go. So what happens if you have a negative exponent? That's the only time these can get kind of tricky. So I have a little bit of a suggestion to kind of help you ease the strain, if you will. So let's start off with finding y prime, since we're finding the first 4. And so essentially, remember, we're going to take this negative 1 here, swing it in front, and subtract 1 up here. And so we end up with, and I'm going to put all of my numbers that I'm swinging in front of the power, I'm just going to keep writing them in front so you can see where I'm coming up with my numbers. So I get a negative 1 in front, x to the negative 2. And so we have to write that without negative exponents. So we get negative 1 over x squared. So there's our first derivative. So then y double prime, I'm going to continue on using this one right here because it's easier to find the derivative, the second derivative, if I'm looking at this one versus this one. Because remember, we never want to find a derivative when it's in fraction form. So I want to start here. So I'm going to take that -1, that doesn't change, but this -2 gets looped in front and we subtract 1 from there. So it looks like the negative, whoops, I changed colors on myself apparently. The -2 gets looped in front, and then -2 minus 1 is -3. So -1 times -2 is +2, and then the x to the -3 goes in the denominator. So this becomes our second derivative. Then our third derivative, y triple prime. I'm again going to continue with the -1, the previous one, -2, and so now this -3 is going to get swung in front, and we're going to subtract 1 from there. So I'm going to add the -3, x to the -4. And so when I multiply these together, I have 3 negatives, so that makes a negative. 1 times 2 times 3 is a -6 over x to the 4th. And so this gives us our third derivative. And then finally, the fourth derivative is equal to -1 times -2 times -3. We're now going to swing that -4 in front and subtract 1 from the exponent, so we get a -5. And so that equals, we have an even number of negatives, so now I have a positive. And then this will be 6 times 4 is 24. So I get 24 over x to the 5th. And that is our fourth and final derivative. So now you get to try. So the first thing you should do, this one has not been written in, try to keep it in your window. This one has not been written in without being in a fraction. So the first thing that you should start with is y is equal to x to the -2. So that's where you want to start. Now you pause the video and find just the fourth derivative. Of course, you're going to have to find the first, second, and third while you're at it. But you don't really have to find the final proper derivative until you hit the fourth one. So go ahead, pause the video, do your work, and restart it. Okay, so y prime is going to equal -2 times x to the -3rd. So there's no need for me to write this one in proper form because I am finding just the fourth. I'm not finding the first four. So make sure you pay attention to the difference in directions. And then y double prime is equal to -2. Now the -3 swings in front, and we have x to the -4th. Then y triple prime is equal to the -2 and the -3, but now the -4 swings out in front, and we have x to the -5. And finally, the fourth derivative of y is equal to the -2, the -3, the -4, and now that -5 gets swung in front and subtract 1 from the exponent. So we now have an even number of negatives, and then 6 times 20 is 120 all over x to the 6th. And there you have it. Good job. So then let's talk a little bit about acceleration. And you will have seen some of these before. So our position function is always just our plain function. We haven't taken a derivative of it. So this function could be anything. In the past lesson that we did, you saw a quadratic function. So it could be any kind of polynomial. Then we went from that position function, which in that respect for the quadratic, which is a parabola, it was a height function. So we went from a height function, which was our position function, to taking the first derivative, which, if you recall, gave us the velocity. And so now that we know higher order derivatives, if you take the derivative of the velocity function, you will get the acceleration function. So what is the difference between velocity and acceleration? So velocity is the rate of change with respect to time, whereas acceleration is the rate of change of velocity. So both have a specified direction, but velocity is measured in units per time, like feet per second, whereas acceleration is measured in units per time squared, so feet per second squared. So they both have direction and they both have a speed, but one is just giving you the rate of change at a specific point in time, whereas acceleration is measuring more of like your force as you're going along. Okay, so let's look at example 4. Make that smidgy bit bigger. If you remember from our last lesson that we could find, so if we're throwing a ball upward, for instance, this is a parabolic arc. So if you throw a ball upward, gravity is going to bring it down. So it's going to look something like this in some sort of arc, right? And you could start from a height of 0, you could start from a height of 10 feet, 100 feet, it doesn't matter what height you start from. If you're going to throw it straight up in the air, it's going to go up for a certain amount of time, and then gravity is going to bring it down. So it always had this, if we're going to look at feet per second, and we're talking about Earth, your height function will generally look like this. You'll always have negative 16t squared, because the negative 16 is the effect gravity will have on the velocity of that ball, the path of that ball. And then the middle term, the coefficient of the middle term, is your initial velocity times t. And then your constant is where you start the path of that object that you're throwing, or the path of the object that's being moved. So a ball is thrown upward from the top of a 160-foot cliff. So this right here is your h sub o, with the initial velocity of, initial velocity of 48 feet per second. So when we write our function, our position function, h is equal to negative 16t squared. Then our initial velocity, which is in an upward motion because we're throwing the ball up, so it's going to be positive, is a positive 48t. And then we were throwing it from the height of a 160-foot cliff. So for instance, in our picture up here, here would be our cliff, let's say. And then we would be throwing it from right here. It's a really sad person. And then this distance up here is 160 feet off the ground. So the question asks, find the height, the velocity, and the acceleration of the ball when t is 3. So the height is our position function. So we're going to put 3 into the position function, substituted in there. Then we have to find the velocity function, which is the first derivative, and put 3 into that. And then we have to find the acceleration function, which is the derivative of the velocity function. So it's the third, it's the second derivative. And so then we have to put 3 into there. So here we go. Step 1. All right. So we've got h of t. So I'm going to write it as h of t. It's negative 16 times t squared plus the 48 times t plus 160. So we're going to substitute 3 in for every t. And if you run that through your calculator, you are going to get 160 feet. So after 3 seconds, the height of the ball is 160 feet. So there's answer number 1. And then number 2, in order to answer number 2, we're going to have to find the velocity function. So we have to find h prime of t, which is equal to, so I'm going to use this function that we wrote up here. So I'm going to find the derivative of that, which would be negative 32 t plus 48. And then we're going to substitute in to the derivative 3 in for every t that we have. So a 3 goes here and here. And so if you run that through your calculator, you're going to get negative 48 feet per second. And so because it's negative, it is a downward motion, which makes sense because it's coming down at that point. Gravity is pulling it down. I imagine if it's at 160 feet, then the 3 seconds went from here to get to that height of 160 again. And so then the acceleration at that point, or the velocity at that point, is now negative 48 feet per second because it is traveling in a downward motion. So then our third step is to find the derivative of the velocity function, which would be h double prime of t, which is the derivative of this function right here. So we get just negative 32. Now there is no t for us to substitute the 3 into, so at 3 seconds the acceleration is negative 32 feet per second squared. So it is important that you add your units of measure into this because there is a difference between the units of measure between velocity and acceleration. So you might want to write here, let's add some writing here. So this one is our velocity. Oh, this was our height. And then this is our accelerate. Oh, yes, acceleration. Okay. All right, let's go on to example 5. I'm not going to make you do a try it on this one. All right, so last example. A little bit of a yippee skippy there for that one. Okay, so this time we have an astronaut standing on the surface of the moon throws a rock into the air. So he's right here, he's throwing a rock into the air. So it should have some parabolic arc. The height, s in feet, so they're going to use s for height instead of h, which is fine, of the rock is given by this. So this is a totally different equation than we have seen before. And so this is something you might want to write down. I'm not going to write it down. I would write it down here. I don't have room as I'm writing it with my stylus, but you can write this down, so you can pause the video, give you time to write it down. But remember, this is the effect of gravity on the moon, so it's quite a bit different than the effect of gravity on Earth, which was negative 16 when we were dealing with feet per second. So on the moon, the coefficient of the t squared term is negative 27 over 10. And so this is our initial velocity. So the astronaut is throwing that rock into the air with initial velocity of 27 feet per second. And he's throwing it from a height of 6 feet, which is about his height, which makes sense. He's not throwing it from the ground at his toes. All right, so the question is, how does the acceleration due to gravity on the moon compare with that on Earth? So there's 3 steps to this one. So step 1, we need to find the position function, the velocity function, and the acceleration function, because in order to find acceleration, I have to get to the second derivative. So we're going to start with our position function, which is the function that we were given. And so that's our position function. All right, so then s double prime. So we're going to take 2 and multiply it to this fraction right here. So when I take 2 and multiply this fraction, that 2 is going to cancel into the 10 5 times. So that is how I am getting negative 27 over 5 t, and it's to the first power because I reduced this by 1. Then we're going to take 1 times 27, and so I get plus 27, and that's it. So this is my velocity function. All right, and then finally s triple prime. So that's our third derivative. I keep saying second derivative, I mean third derivative. I think I've said that twice now, so sorry. So this is equal to, so I'm going to take this exponent of 1 and multiply it to this, and this becomes 0 and goes away. And of course, the derivative of this is 0. So for our acceleration function, we get just a constant, which is negative 27/5. So this is our acceleration function. So then step 2, we need to look at that acceleration function. So if we take negative 27 over 5, it might make more sense if we divide it out and look at it as a decimal. So if you divide that out, you're going to get negative 5.4, and that is feet per second squared. Okay. Then we're going to take that value right here, and we're going to use that in our third and final step. We're going to compare that negative 5.4, that acceleration function, to the acceleration function in example 4. So if you go back and look at example 4, if you look at the third step in example 4, the acceleration function, that was negative 32 feet per second squared. So if we put the negative 5, whoops, I haven't changed my color. So if we put the negative 5.4 and put it over what we got from example 4's acceleration function, which was negative 32, and this is also feet per second squared, so the units are going to cancel out. If you divide those out, you get a lovely decimal, which is 0.16875. So that is about that much of the acceleration on Earth. So that's similar to a fraction. It's about 1/6 of the acceleration on Earth. Now, you might prefer instead to call it as a percent, or if we wrote that decimal as a percent, it would be 16 point, let's just write the whole thing out, 875% of that on Earth. Because most of you will have gone, how on earth did she know it was 1/6? It's not exactly the same decimal as 1/6, but if you take 1/6 and divide it out into your calculator, you'll see that the decimals are very similar. All right, so that is the lesson for today, and you will do your homework on this lesson next. So have a great day.